Folks, this is a short video segment on performing a single degree of freedom uh, example using the FEA capability in the 3D experience release 2023X. Now, I already have two videos where I've shown how to calculate natural frequencies of a single degree of freedom system. This one is about the steady state dynamics. In other words, the load applied to that single degree of freedom is a sinusoidal in the form that you see here. Now, keep in mind that this is a very simple problem. It's like doing it with FEA in 3D experience is like trying to kill a fly with a cannon. However, uh, I want to show you how this is performed because if people cannot do a problem like this, in all likelihood, in a more complicated situation, uh, they're going to have even more problems. Okay, so these videos are intended for people who are either novice to 3D experience or people who already know how to do Abacus CAE and they're switching to 3D experience or they're trying to replicate what is done in the CAE, Abacus CAE, in the 3D experience. Keep in mind that the solver in 3D experience is actually, FEA solver is actually the Abacus program. And of course, the CAD part of it is the CATIA V5/V6. The problem that I'm going to be doing is this particular single degree of freedom system, which incidentally I've taken from a website here, a YouTube channel there. And this person, this professor, is doing all the steps in the Abacus CAE. So it is a good idea to, if you're interested, to also look at the other one to see what are the differences between the interface in the 3D experience and the interface in the CAE program. Uh, Now, the dramatic, the solvers are the same. It is the same Abacus program, but there are dramatic differences as far as the interface and icons and functionalities between the two software. Um, Now, the purpose of this channel is expose people to the 3D experience platform. Now, when you do this thing, if you need to do the hand calculation, you find in any standard vibration, third-year vibrations undergraduate class or textbook, and you need the natural frequency and you need the frequency ratio, omega over omega n. Omega is the frequency of the applied load or the driving frequency, and the F0 is the amplitude of the sinusoidal load. Now, in these vibration textbooks, you find that the response of the solution looks like that. There's an amplitude big X, and there is a phase that you can calculate based on the information that was derived here. And when you do that, you're going to come up with a plot of amplitude, or in this case, non-dimensional. Sorry, the uh, dimension dimensionalized amplitude. So notice that F0 over K is the static deflection, and this is the dynamic magnification factor, and that's how you get the amplitude of the dynamic problem. All right, so let's go ahead and do that. We are here. Okay, let me start a part file. And I'm going to place my spring between 2 points which are lined up along the y-axis. So my first point is going to be the support which is over there, and the second point I'm going to make it 20 millimeters on the y-axis right there. All right, uh, that's pretty much it. This is our model. So now we're going to go to structural model creation, standard icon, accept the defaults here, and then place the mass. You have to go to the abstraction tab right there. See that? The abstraction tab. And towards the middle, you have the point inertia, which is a point mass basically. Click on it and put 2 kilogram and then place it right at that location. And if you looked at it closely, you see that there's something that looks like a weight here, which is supposed to be our mass. Now, for the spring, I'm going to go to the connections tab right there. See that? And towards the right, on the third one from the right, you have a spring and rigid connection. Of course, we want spring. You click on it, and since I don't want everything to be collapsed to one point, so I'm going to select as the support one this endpoint, and as the support two, not the ground, you select it. You select the support two so that this becomes actually blue, and then you select this point, and it places the spring here for you. You can see that right there. Okay. Now the length of this is immaterial for us at least, and first of all, the stiffness is 4 kilogram uh, uh, kilogram per second squared, which is essentially Newton per meter. Okay. Now, in order to include the damping here, so a single spring dashpot element, basically, you have to select this enable advanced behavior, and you click on the pen. Now notice that ordinarily if you click on the elasticity, it tells you that it's along the x-axis, but this x-axis is the local axis. It has nothing to do with the fact that I place my spring along the y-axis. Don't worry about that. There's nothing else you can choose here. And the 4 is what I inputted a minute ago. Now to specify damping, ordinarily you have to go to this box here. You see that? Any of these white boxes, this damping box, but it doesn't work. You have to go to the text and do this. You go to the right of it a little bit, and now you select it, select FX. This is a viscous damping, and for the damper value, you put down 1, and we're good. This is actually our finite element model. So now, ordinarily, when I'm done with my model, I go to structural scenario creation. That's what I've been doing in the last 2 years, 3 years. But I've begun switching to this mechanical scenario creation because there's a lot of stuff that you can do here that cannot be done in structural scenario creation. You click on it, and make sure that you choose use the pull down menu to select structural, because if you do general, there will be some icons that is going to be distraction, flux and temperature and things like that. So I changed it to structural, and for the finite element model, you use the pull down menu and select the one that we just created, and then we say okay. All right. Now, I'm going to do a natural frequency calculation first. That's needed to do modal dynamics, so or steady state dynamics. So first thing, I'm going to go and select on procedure. On the right hand side, you scroll down here, you select frequency step. I'm going to ask to the default 10 frequencies to be extracted, but this is a single degree of freedom system. Therefore, there's only one frequency basically. So, but I'll just leave the default here. Whatever find it will find, and obviously the only one that's of interest to us is natural frequency, which is 0.225 hertz in the right there. This is the only one that's relevant to us. And say okay. Now, let's put some restraints here. Okay, so the restraints are under boundary condition. This is fixed displacement. These 3 points, sorry, these 2 points, these are pin. This point is pin, and this one is can only move in the y direction. So you have to do it twice. Rotations are irrelevant here because we're dealing with the extensional spring. Excuse me. You click on this thing again. You select that point. So X is fixed, Z is fixed, but Y is free because it's going to vibrate along that. Rotation is irrelevant. Now, notice that these things are actually created in our frequency step right there. And of course, they're also over here, which in the language of Abacus CAE, these are probably equivalent to the initial or base state information. Now, let's run it, and then we come back and add the modal dynamics after that, or the steady state dynamics after that. So we go to the simulation tab. Let's do a model check first of all. Model and scenario check. It worked. and do the simulation check. Anything that's major is going to pop up here. I don't anticipate any issues. And the only frequency, once this checks out, then we're going to simulate it, and the only frequency that's going to come up is going to be 0.225 hertz. Okay, so let's give it a minute or so. Yep, this one is done, and now we're going to simulate. This is simulated. Notice that all we're doing here is finding the natural frequencies. That's all. There's only one of them, of course. There is a warning. We're going to check it out. It says only one eigenvalue will be extracted because of the nature of the problem, of course. And notice that it did actually, you can see that right there, 0.225 hertz. If I go there, yeah, 0.225 hertz. Good. Now we're going to go back to the scenario right there, because right now we are in results. We go back to scenario. And over here, we're going to say insert a direct harmonic response step, which is essentially steady state dynamics or modal dynamics. You click on it. Now, the frequency range is going to be between 0 and 2 hertz with increments of 0.1 hertz. Let's make it 0.1, because otherwise this graph, the resulting graph is not going to be, is going to be jagged. Okay. Good. And then we say, okay, we're going to apply our loads to this point. So under loads, it's a concentrated force to that point, and it's going to be in the direction y, which is 3 newtons. Now, if you wonder where that's coming from, unfortunately, I forgot to put it in here. Oh, right there, right there. F0 equal to 3 newton. Okay, and in my calculation, of course, it's right up here. Good. So in the y direction, okay, because the load is applied actually in the true y direction, it's not the local direction. And then we say okay, and yeah, that's pretty much it. So we go to a simulation. Let's ask for some data, because I want to be able to plot the information about this point. So we click on the output and try to select this point right there. And displacement is what I want, translational displacement. That's pretty much it. And it's the not field one, history. Okay, history, every increment, and we say okay. Good. Let's do a model and scenario check. I don't anticipate. Oh, yes, 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 yes. Let me show you something. Actually, this will bomb out, and it's a good idea to do it because I want to show you something. Close. Let's do a simulation check. I think it's worth seeing the failure here. It's running. It's actually doing a check, simulation check. Okay. And finally, we run it. We simulate it. This is the last step. and see what goes wrong. It's something that I didn't anticipate, but once I realized what the issue was, it was easy to fix, but I didn't expect this. For those people who watched that video on the abacus that I basically extracted this tutorial from, you see that there's significant differences between what is done there and what is in 3D experience. The problem is the same, the icons are the same, the interface, a lot of it, they have shared stuff, but already you can see there's 207 warnings here. Now notice that what happened is that this is the frequency step that we already had. Let me close this for a second. If you go to the dynamics, okay, model dynamic, uh, and you can plot things, there is no issue, but let me go ahead and do a history plot here, right there. And let's do the translation and the magnitude and say apply. Now that sure doesn't look like this. As a matter of fact, if you look at the numbers here, it's e to the 18. Something did not work. And let me close this and close that and show you what happened here. In the steady state dynamics, the information about the displacement or the restraints is not transferred. See, there is these things. Remember, I pinned the left point and I made the right point where the mass was along the y-axis. That information is not present here. So let's go back to the scenario here, back to scenario, and do it again, because I mean obviously it's up here, but these did not go directly to the direct harmonic response. So let's do it again. On the boundary condition, okay, so this same point, once again, we are in direct harmonic response now, all pinned. This third one is exactly like the first one, and do it again for this point. The only difference is that let me try to pick this point. If it's blocking you, let's hide some of the stuff right there. Okay, does not move in X, does not move in Z, rotation irrelevant, but it can move in Y. So here, essentially, we have duplicates of these things, which are now in the direct harmonic response. So let's go ahead and run it, okay, simulate it. I'm not going to do a model check. Let's go ahead and simulate it, and I anticipate things to be okay. Let's find out. And naturally, the way I'm doing it, it does the modal dynamics again. In other words, find the frequencies one more time, but it's a simple problem. It doesn't matter. We still have these warnings, no problem. Let's just wait and plot that thing and see whether we actually get something that looks like that. It's a good idea to go and check these warnings and see what they are, but let's wait and find out how the plot looks like. Okay, I'm going to close this. I'm going to go to my results here. This is the XY plot that I created. Double click on it and apply. And there we are. In fact, if you look at it, the peak is at 0.225 hertz, okay? And it is matches about 2 millimeters, because this is in unit of millimeters, so it matches 2 point something. This is in meters. What I have here is in millimeters. You can also plot the phase angle. Let me see for a second. Not there. Oh, maybe in there. Yeah, it's just a magnitude. You can plot the phase, but I don't think I requested it, so we just leave it the way it is. Anyway, there we are. So we solved this problem as a steady state dynamics, or I think this guy is calling it, what is that, direct harmonic response. So I will have one other video following this where I integrate this thing in time and we look at the time response instead of the frequency response of the problem. Good luck.